Well, just a quick little look here. I just thought this was interesting because this is obviously it's a little 12 volt 1 amp 110 volt switch mode power supply I picked up off Deal Extreme. Kind of amusing. You can see that they obviously assembled it with the coating on the coating on the aluminium base side pins. Also, you can see that apparently China has become too cheap for screws because it's held together with these little indentations. You can also see that they put it together before peeling off the protective plastic. The thing that I thought was really interesting is apparently the people who scratch the name off chips have gone one better, and they have purchased the chips before they've been marked. So what we have here is a board with a switch mode controller IC that hasn't had the name scratched off. It's never had the name applied, which is something I hadn't seen before, so I thought it was kind of intriguing. There's no markings on there. So here's a closer view, and you can see that that is an entirely unmarked dip package. So apparently, rather than trying to scrub the ICs off, presumably this is a Chinese designed controller, they've simply elected to purchase them before they've marked them. Which is kind of surprising, because this is an otherwise, it's not a horrible switching controller. You can see they've actually bothered with, so they've bothered with trenching out this section here to maintain clearance, and it actually has a real glass fuse, though it's with, it's just a lead-ended. Soldering's a little sloppy. You can see that like this cap here started to kind of tilt when they were wave soldering it, but it didn't pull the legs out. It looks like they trimmed the legs after they soldered. It's a fairly nice little power supply. I'm not too sure what this, solder mask is here for. Maybe they're trying to, basically increase the breakdown voltage of those little gaps. From an electrical perspective, it's extremely simple. Alright, well here's basically here's the schematic of this module. Sorry, it's a little messy. I wasn't too sure how it was going to come. I should have moved the IC over, but well, that's what you get when you're drawing a schematic while figuring out what the schematic is. A couple errors on here. I put the diode in the wrong place. This diode and this resistor are reversed. But on the whole, you can see it's a very simple system. Got your line in. Comes into the bridge rectifier. You've got a big bulk bypass cap, so this rail here is going to be like 160, 170 volts. Got one terminal lead goes right straight up to the transformer, and then in here there's going to be a big switching transistor. So it's an integrated switcher. And then you've got so you have this big resistor here, which is this silver resistor here, which is going to be for current sensing in the switcher. So that's basically for sensing your current in your transformer windings. You can see here we've got an LED going into, I'm guessing this is a phototransistor, it could be a photodiode. There's a capacitor across it, which is just going to be loop compensation. So that is this capacitor right here. And you can see that here are your two opto terminals, and one of these traces runs to one terminal, the cap, and then this here is ground, because you can see it returns back to this negative node. So then that just goes into one of the pins in the IC. So presumably, assuming this is a phototransistor, there's going to be a pull-up in there, and then this goes off into the feedback mechanism. You've got a capacitor here, either for loop compensation, slope limiting, could be an internal oscillator. And then one of the interesting things you have here is you've got a secondary, a second primary winding. A couple windings here, a diode and a resistor, though again, these are backwards because I am lame. And then you've got a little cap here. This is a 25 volt cap. So presumably what happens is your IC actually runs on this capacitor. And then what happens here is, ARG, more fun capacitors, or excuse me, more fun camera issues. So the interesting thing here is that you can see that, obviously, once the system's up and running and the transform, you're driving the transformer, you're going to get plenty of, you'll get plenty of feedback from this here to charge, to keep that capacitor charged. The interesting thing is, how does the IC start up in the first place? Because obviously, you need power here, this needs to be charged up for the inductor to work, for this switch to be able to be biased on to switch the transformer, which would then, put charge in the capacitor. So one of the things of interest is that you can see here that there is a just a resistor here going straight into the IC, and that's interesting because it's this part here. It's a fairly large, also fairly high value. It is red, green. So that is 220 kiloohms. So what I would guess is happening is that it just switches that to the, basically charges this capacitor straight off the line voltage for a short period of time, and I would imagine that you get a fair amount of dissipation here. And then once the system's up and running, it may, basically disconnect that. I'm not sure. It's some sort of startup condition mechanism. And then, on your output, you've just got a single, it's half-wave rectified. You've got a capacitor here, and one of the things is, it's got like a connection straight to the terminal of the capacitor, and then it runs from the capacitor terminal on. You've got a series inductor. Kind of interesting is the fact that it's tapping off the LED voltage here. And then, so one of the other things so what's happening here is, you've got a resistor divider going into the reference of this. So basically, the way these work is that when this voltage here exceeds, some of these, they vary, they're 2.5 or 5 volts. Basically, when this voltage here exceeds the internal reference, this begins to conduct. So what will happen is basically when this voltage here reaches a certain point set by this resistor divider, this will begin to conduct, which will turn the diode on. So and then that will pull this pin down. So presumably that will change the duty cycle or stop it, depending on how the feedback works. But so again, basically the voltage is adjusted, and you can see there's a pot here, and that basically just adjusts the ratio in this voltage divider by a small amount to adjust the output voltage. And then the real magic in this circuit, and the thing that, it's a very simple circuit, but the real tricky thing is to get it to properly be stable, which you can do by loop analysis or just experimental testing, which is just the value of these capacitors here and possibly this capacitor. Honestly, this looks like a bunch of really common, there's a number of fairly common little switch controller ICs that look like this. Have a similar topology. You've got a feedback node and, some current sensing, and you can see that there's a ground connection just straight up to the IC. So, and then these are the little, I think these are probably film caps. The one thing of note is that this capacitor here is ceramic, whereas these two are film. So the real probable loop compensation is going to be these two devices. And this may just be to limit sensitivity to spurious stuff of some sort. I'm not totally certain. The TL431s are an interesting part. It's basically a it's a very accessible air amplifier. Internally, they look like a so you can think of them as an op amp, an NPN transistor, and then so you have your plus and your minus input, and the minus input goes to, say, 2.5 volt ref. And this here, so you have, this is basically the top node, this is basically the bottom node, and incidentally these are connected to the op amp like so. And then here's your reference input. So you can see that if this voltage here exceeds this voltage here, the output of the op amp will go high, which will turn the transistor on, which will pull this down. So basically, one of the things, the common connections for the TL431 is to simply tie these two nodes together. And then what will happen is if this voltage here ever exceeds the voltage of this reference, no wait, excuse me, I'm being stupid. No wait, that would work. Yeah, so if that voltage ever exceeds that, it begins to conduct. And then, if you want a spurious voltage, if you want a different voltage, like if this is 2.5 volts and you want 5 volts, you simply have a resistor here and a resistor here. So And you just tie this to this node down here. So then what happens is the voltage here is half of the voltage here, so that when this reaches 2.5 volts, this is at 5 volts, and then it begins to turn on and pulls it down. So what this forms is a shunt regulator. You know, basically it acts like, again, one of the things it's billed as in its datasheet is a programmable zener. So, you know, basically you can set this up so that it'll regulate the voltage across the two terminals to, you know, whatever voltage you want. So that's what you can see they're doing here. They're using it as an error amplifier, but they're, you know, the terminals are being driven slightly differently. They're not, you know, basically as this voltage increases, the extent to which this transistor is turned on increases as well. You know, to eventual, you know, an eventual minimal voltage drop across it of whatever the few, you know, VF drop, V forward of the various devices in there are, probably a volt or two. Actually, the data sheet should have it. Yeah, actually, that's not bad. I drew that from memory. So there's your functional diagram. You can see other stuff. Reference, you've got a, where's the voltage reference? You've got a current mirror, various stuff. I mean, it's a pretty simple circuit, so you can see 37 volts, 150 milliamps, 36 volts, 100 milliamps. Reference voltage is 2.4, so it's typically 2.490, basically 2.5 volts. Comes in a lot of packages. Off-state dynamic impedance, 0.5 ohms. So as you can see, now we're looking at a different voltage. So you can see a minimum cathode current for regulation, ergo it has to have some power flowing through it for it to properly regulate. Off-state cathode current, 1 microamp. Geez, how many different versions are these? So as you can see, these are all for slightly different model number permutations. Yes. Blah, blah, blah. So yeah, you can see that here, you know, basically when you tie the adjustment to the cathode, you basically get whatever the reference is. You know, you can see test circuit for VKA is equal to Vref. That doesn't make any sense. That doesn't make any sense. Oh wait, no, this is for that circuit. This is test circuit for VKA is greater than Vref. Test circuit for I off, so presumably in this situation VKA is less than, or so in this situation whatever VKA is has to be less than Vref. Okay, yeah, here we are. So you can see here that with the input, with V on, it pulls down to 2 volts, and with V off, it's at VI bat. So basically what they're saying is that approximately when the system's fully saturated, it drops approximately 2 volts. So that answers that question. So basically, another thing of interest is I don't see any current limiting mechanism in here. That's kind of, hang on, did I just miss it? Yeah, I did. Okay, so it looks like I'm being incredibly lame, and there is a resistor here. So that makes much more sense. So you've just got, you know, basically, so when this voltage here is too high, you know, this will fully saturate, and you'll basically have just your straight up supply across here. Turn the opto on hard. You know, again, this can sink a lot of current, and this resistor is looks like yellow, brown, brown. So that's going to be so that's going to be 4100 ohms, or excuse me, 410 ohms. So yeah, it'll, you know, then you can push a fair amount of current through there. I mean, most optos are rated at 50 milliamps. They're a lot higher current than straight up LEDs, presumably because they're infrared LEDs. Yeah. So anyways, it's, you know, it's a fairly simple circuit. It's a little interesting to just kind of look at how the internals work. Surprisingly decent for, like, this. I think this whole thing was, with the kind of amusing box, was literally, I think, $4 or $5. Claims 12 volts at 1 amp. It's kind of funny because it's in a very nice aluminum box, but they're not heat sinking to the aluminum at all. It's entirely, you know, again, the switching element to the IC, which despite the fact that it's entirely unlabeled is, not heat sunk to anything except maybe the transistor, or excuse me, the transistor. You can see two of the leads of this are actually the switching leads. It's also kind of clever in that it's held together with a grand total of one screw. So you can see it's got these two little tabs that hold the board in on one end. And then you have just a screw that goes in on the other. So I bought this together with like an LED strip to use for some under counter lighting, or some under cabinet lighting for a counter. And I think it'll work fine. You can see they're kind of clever. They have holes and big indentations to hold the thing together rather than bothering with screws. So it's all spring force. And they've got little cutouts for screwdriver access, and they got nice labeling. It's a fairly satisfying little switcher. It is XINYUANYANG, yin yu yang. Got a little power LED, and then it's just got two screw holes for attaching to whatever. So one thing to note actually that I just noticed is that it appears that there actually is a grounding for this single chassis ground pin, so that you have a ground here, and it actually appears to be fairly strongly strapped to this basically this threaded insert, which seems to have taken the plastic with it. It's still got plastic poking out of it. So yeah, there's a quick little reverse of a very simple switcher. Hey, this is just a quick follow-up. So I was curious about the fact that I couldn't see how the switcher from the little power supply started up. So I was just looking around, poking around at a bunch of data sheets in various companies. This is not the controller from that particular power supply, but it's similar. So you can see actually what they do here is so this actually doesn't have the bridge rectification, but you've got HV and you've got your ground. You can see that they've got a similar mechanism where there's basically one resistor, or basically a connection directly to the IC from the high voltage, despite the fact that this is a low side switching device. So in this particular data sheet, as you can see, that they've got an external power device rather than the other one. So this is a higher power, basically switch mode controller. But what they have is, if we go down to the equivalent circuit, is you can see that what they've got internally is a current source. Sorry, I just got an email. The current source that dumps into the local 12 volt VCC. So you can see it's got VCC management, VCC off. So basically, when VCC goes above 12.6 volts, this switch opens, which basically means it no longer is dumping charge into this the capacitor connected onto this terminal. Again, if we look up here, so that is pin 6. So if we look here, you can see that on the secondary, the second primary winding, they've got the similar diode and resistor system, and then they've got VCC cap, which goes into here, and then there's a net label which goes over there. But that's another issue. So what happens is basically before it has enough power to turn on the main switching device, what happens is this current source dumps current into that capacitor to bring the voltage up enough that the VCC min, it exceeds VCC min, and then the system starts, then the system presumably starts, that kicks in the startup timer, which then starts the oscillator, which is somewhere over here. Where's the oscillator? There it is, right there. Never mind. Derp. So that starts up the oscillator, and the whole system starts running. And then once it's running, VCC is maintained apparently at 20 volts by the effectively having this Zener diode here, which would just basically be a simple shunt regulator. So I would imagine that to make this work properly, you have to size this resistor here so that you just have a little extra current. So maybe your current flow through this diode is probably just a milliamp or two, because you can dissipate a lot of power there if you're not careful. With 20 volts and 10 milliamps is that's 40 milliwatts. So that'll get pretty warm, considering that this is in a depth package. You don't want more than 5 or 6 milliamps. because that would be, you don't want to go over 100 milliwatts in a DIP package, in a DIP 8 package if you can avoid it. And you also have all the, whatever energy you're going to be losing through the driver and all the other crap going on in here. Another thing of interest is if you look at this actually is kind of interesting in that it doesn't have any loop compensation, but you can see it uses a similar mechanism where you have a phototransistor, and then in the IC, whoops, I don't accidentally hit the power button. So then in the IC on the feedback pin is a pull-up and some other stuff. So basically they've moved most of the components you'd need for that into the IC, so you just need a single phototransistor and maybe a loop compensation capacitor. So that's a pretty, it's an interesting example. This is an ST part, an on semi part, and they make a number of parts that have similar topologies. Though this is the one that had the, an equivalent, circuit diagram that was the clearest. A lot of them have a whole lot of stuff going on inside. On that little switcher, I think that they probably don't have this current source here. I think it's probably just a switch, and then you have an external resistor which dictates the current, which of course also means that the current flow is going to be different depending on whether you're on 120 and 240 volt line. So, it's a neat little system. You can kind of see that basically this is probably just a couple comparators. I'm not too sure what delineates between VCC min and VCC latch. But in this situation you've just got a FET, a gate driver here, and that uses a switching FET. And then you can see there's a lot of internal references, other stuff. But this is not necessarily relevant. It's just kind of the topology of using the second primary winding, or two primary windings, for generating, this low voltage here. I'd imagine that another issue they'd have here is that, basically well, I guess it depends on the duty cycle, but I would think that you would get, never mind, I'm being stupid. I was just thinking about the effects of putting it on 240, but the fact that, you're going to need to compensate for the output voltage to be the same anyway, so. And you can see here that the way this works is basically just whenever the voltage, you exceed the voltage of this zener, the diode begins to conduct, and therefore the diode lights up. But it's much simpler than the air amplifier mechanism on the other IC, but either one would work. So anyways, that's just a cool, a neat little example of how, one of the possible ways that direct line connection, could possibly work.